Welcome back to this module on pipelining. In this lesson I will describe a canonical pipeline consisting of 5 stages. Oh, but wait a minute, this is not a course about the history of laundering, is it? What does this have to do with computer architecture? How can we apply this idea of pipelining to the execution of instructions? In the canonical computer pipeline there are 5 stages. In the first stage, the instruction fetch, or abbreviated as IF stage, the instruction to be executed is read from memory using the program counter as the instruction address, and the PC is incremented so that it points to the next instruction. Since all instructions are 4 bytes in MIPS, incrementing the PC means adding 4 to it. The second stage is the instruction decode, or ID stage. In this stage, the instruction is decoded in the control unit to determine what needs to be done. But also, the source registers are read from the register file in case we need them. Now we understand, at least partially, the beauty of the MIPS instruction set. Because, as I explained in a previous lesson, the source registers are always in the same place in the instruction format, namely in the RS and RT instruction fields, we can read the register file before the instruction is decoded and we know what the instruction needs to do. The third stage is the execute stage. In this stage, the operation that takes place depends on the instruction. This is possible because the instruction has been decoded in the previous stage. R-type instructions such as add, subtract, but also logical operations such as OR are executed. For memory accesses, loads and stores, the effective address is computed. This consists of adding the base register RS to the 16-bit immediate offset encoded in the instruction. Third, for branch instructions, the branch condition and the branch target address are computed. The branch condition determines if the branch should be taken or not. For example, the branch if equal is taken really takes place if its first source register is equal to its second source register, and this needs to be calculated. The branch target is computed by adding the offset to the program counter plus 4. The fourth stage is the memory access stage. In this stage, a load reads from memory using the address calculated in the previous stage, and a store writes to memory using the calculated address. For all other instructions, nothing happens in this stage, but they still have to go through this stage. This is because the instruction pipeline needs to stay synchronous. The fifth and final stage is the write back stage, or the WB stage. In this stage, instructions that write back a result to the register file do so. Examples of instructions that do not write back a result to the register file are branches and stores. Now that we know the 5 stages in the classic canonical pipeline, let's see how each individual instruction is executed. Here's time divided into clock cycles, CC1, CC2, etc. In the first stage, corresponding to the first clock cycle, the instruction state is fetched. In the second state, it is decoded. As I just explained, in this stage, the register file is also read. In the third stage, the instruction is executed. As just explained, the operation performed in this stage depends on the type of instruction. In the fourth stage, the memory access takes place, in case the instruction is a load or a store. And finally, in the fifth clock cycle, the result of the instruction is written back to the register file if needed. But pipelining does not accelerate the execution of individual instructions. It increases instruction throughput, the number of instructions that are completed per time unit. Let's see how. Let's consider the execution of a sequence of 4 instructions. Here's again a timeline, and here vertically are the instructions. In the first stage, we fetch the first instruction. Then in the second cycle, we decode the first instruction, and at the same time, we fetch the second instruction. Similarly, in the third clock cycle, we execute the first instruction, decode the second instruction, and fetch the third instruction. Then, in the fourth clock cycle, the mem stage of the first instruction takes place, the execute stage of the second, the ID stage of the third, and the fetch or instruction fetch stage of the fourth instruction. Then, in the fifth clock cycle, the first instruction completes by writing back its result. The second instruction accesses memory if applicable, the third instruction is executed, and the fourth instruction is decoded. And so on and so forth. We see that in the ideal case, every clock cycle one instruction completes. Because there are 5 stages, the ideal speedup would be 5 compared to a non-pipeline processor. In practice, the speedup will be less because first, the amount of work in each stage is not perfectly balanced, and second, because there are some issues with pipelining that cause the pipeline to stall from time to time. More about these issues I will explain in the next lesson. I'm going to draw a block diagram of our first processor, the 5-stage pipeline processor. Furthermore, I am going to focus on the data path of the processor. The data path is the part of the processor that performs operation. It is controlled or steered by the control part. Data path and control together form the processor. This is the first part of the data path that performs the instruction stage. The program counter is used to address the instruction memory, and the instruction memory returns the instruction the program counter points to. The instruction is stored in a pipeline register called IF/ID. It is called that way because it separates the IF, the instruction fetch, and the instruction decode ID pipeline stages. At the same time, the program counter is incremented by 4 and the new sequential PC is latched in the PC register. Note that the PC and the instruction fetch, instruction decode pipeline register both have a small triangle drawn at their bottoms. This means that these state elements are clocked. They only change their state or content at the end of the clock cycle. For example, on the falling edge of the clock cycle. This is the part of the data path corresponding to the instruction decode ID stage. While the instruction stored in the IF/ID pipeline register is being decoded in the control unit, which for simplicity is not shown here, the registers RS and RT are read from the register file in case we need them, and stored in the IDX pipeline register. At the same time, the 16-bit immediate, shown here, encoded in the instruction is speculatively sign extended to 64 bits. Finally, the destination register RD and the next sequential PC are passed on to the IDX pipeline register because they are needed in later stages. This part of the data path corresponds to the execute stage. The operation the arithmetic logic unit or ALU performs depends on the instruction type. For R-type instruction, it performs the operation specified by the function field. For loads and stores, it computes the effective address by adding the base register RS read in the previous stage to the constant immediate sign extended in the previous stage. Finally, for branches, it computes the target address by adding the next sequential PC, PC plus 4, to the offset contained in the instruction. This offset is multiplied by 4 since it corresponds to a word offset, but for simplicity, this is not shown in this figure. In order to perform operations with different operands, there are two multiplexers in front of the ALU inputs. The top multiplexer selects between the next sequential PC for branch instructions and register RS read in the previous stage, which is needed for all other instructions. The bottom multiplexer selects between register RT, which is needed for instructions having two register source operands, and the sign extended immediate contained in the instruction, which is needed for loads, for stores, immediate type instructions, and branches. This data path, as shown here, supports only one branch instruction, the branch if equal to 0. This branch instruction tests if the RS register is equal to 0. This is done by the yellow block labeled 0, and if so, jumps to the branch target address. In this block diagram, the branch target is calculated by the ALU. At the end of the clock cycle, all intermediate results, the outcome of the 0 test, the ALU result, and also the contents of register RT, since this is the register to be stored in case the instruction is a store, are latched into the XMEM pipeline register. In addition, the next sequential PC and the destination register RD are also passed on from the IDX pipeline register to the XMEM pipeline register. This part of the data path corresponds to the memory access stage, the MEM stage. Loads and stores access memory using the effective address, calculated in the previous stage. If the instruction is a store, the data to be stored is on this line. If the instruction is a load, the data loaded is latched into the MEM write-back pipeline register at the end of the cycle. Branches also complete in this cycle. To be precise, if the outcome of the 0 test in the previous cycle is true, indicating that the branch should be taken, this multiplexer does not select PC plus 4 as the next program counter, but the branch target address, which has been computed by the ALU in the previous stage. In fact, we also need to solder the output of the multiplexer to the PC register, but for simplicity, this has been omitted in this diagram. If the instruction is an R-type instruction, such as an add or a subtract, the ALU result is simply routed around the data memory as indicated by this line. Finally, the write-back stage. If applicable, the result of the instruction is written back to the register file. If the instruction is an R-type, such as an add, subtract, or logical OR, the result of the ALU 2 cycles ago is written back to the register file as indicated by this line. If the instruction is a load, the data read from memory in the previous cycle is written back as indicated by this line. In both cases, the number of the register to be written is given by the RD field, which is on this line. I understand that this is a lot of detailed information, and I don't expect you to understand in every detail immediately, especially if this is the first time you see such a block diagram. The most important point I want you to take home are, first, we can split the data path into cycles corresponding to stages by inserting pipeline registers between the stages. Second, the register file is read in the second stage and it is written in the fifth stage. Third, branches actually take place in the MEM stage, in the fourth stage, and at that time, 3 sequential instructions have already been fetched. This completes this lesson. Thanks for watching. In the next lesson, I will describe some features of the canonical pipeline and explain what pipeline hazards are. Stay tuned.